Obsidians can tell us about the cultural landscape. And then he gave me a brief thing to read to you. William Whitehead, as a doctorate in anthropology and a senior lecturer here at UW-Ottawa. By training, he's an archaeologist specializing in archaeometry, paleoethnobotany, and South American archaeology. He began his early career in the Midwest investigating archaic and woodland cultures in Missouri, Illinois, Arkansas, and Kentucky. Then as a first-year student in graduate school, started working in Bolivia and Peru on formative and middle horizon cultures in and around Lake Titicaca Basin, which led to his dissertation title, Exploring the Wild and Domestic, Paleoethnobotany of
Chiripa.
Thank you. A formative site in Bolivia. Highlights of his career are seen in the publication of many co-authored research reports in archaeological journals, conducted research in America and South American museums, and directing undergraduate research at the institutes he's been employed in. An alumnus of Washington University in St. Louis and the University of California, Berkeley.
Yeah, that was
like Mad City, Madison, although bigger. William has been raised in the liberal arts tradition and has been teaching as a lecturer at UW College since fall of 2006. Today's talk will be about recent work in San Pedro de Atacama with multi-institution research group founded 4 years ago to investigate material culture and social interactions in South Central Andes.
cool.
Without further ado, we need
Good. All right.
Thank you, buddy.
Thanks. All right. So, thank you for coming. I'm very happy that you're all here. And the objects of interest today are these things: rocks. This is obsidian. This is rhyolite, and this is granite. They're all chemically the same, but they form under different geological conditions. Each one of these contains inside of it trace chemical signatures, rare earth elements, trace elements, metals, some rare alkalines that allow you to trace this object to a locality on the earth. That's important. So if you'd like to see these different rocks and just see what differences in pressure, temperature, and cooling rate can do to crystallization, and exactly the same stuff, just like, say, sugar. Here it is. Let's take a look at that. And be careful with the obsidian. It is very sharp. It's glass. Glass meaning that is an amorphous solid, snapped together with very little crystallization. All right, now, where's my little clicker? This is a bit of a long talk, so please bear with me. It has an outline. Okay, and do you want to play it nice or not? Go what? I'll just have to hit the button. Come on, play nice. Go. Okay. Doesn't like that either. How about that? Okay.
Spacebar time.
Now. You want to take over that? That's not good. Well, we can do it this. You know what do you think? Why would spacebar not be working?
Almost.
Take that off. You know what? We can just do it. Do you want to try this a little bit?
Safe?
Okay.
Stand safe.
All right. Well, we're trying to figure out the technical problem. The objectives are to use a geologically placed material to investigate people's use of the landscape. And in archaeology, what'd you do?
Magic.
Okay, magic. Great. I'm good with magic.
Turn the machine off.
Yeah. To understand how people did things in the past, and we have to use quite a few methodological and theoretical tricks to understand what people do when you can't directly observe them. Archaeology is anthropology of people who can no longer tell us about what they're doing. It's using people's material culture, the stuff that we make, that we leave behind, to try and understand their cultures. So the objectives here were to use this geologically traceable material to figure out interactions in the region of San Pedro de Atacama. And of course, to use several techniques, and I'll talk about those techniques, to look at archaeological and modern obsidians, then to discover new obsidians in the San Pedro de Atacama region, and then use this obsidian data to talk about local and non-local interactions. And this is part of a larger group of studies where I believe a couple of years ago, or even just last year, I gave a talk about using some of these techniques with ceramics. So we're doing the hard stuff first, and this is the easy stuff actually by comparison. So let's go to Google Earth and look at what this place looks like. So if you look at the San Pedro de Atacama region from space, you'll see that it is in northern Chile, and of course we'll skip out a little bit here. And yeah, here we go. So there's South America. Here's the San Pedro de Atacama Basin. And geologically, it's very important because just like the Salt Lake Basin, just like the Titicaca Basin, there's very few outflows for any materials, i.e. water, that flow into that basin. Therefore, it is a receptacle for everything geological that is being washed in. If you don't know this, I'll tell you that one of the largest sources of lithium carbonate in the world is residing in the bottom of the basin, where all you need to do is pump water into the ground, suck it up, dry it out, and then you have almost pure lithium carbonate.
What's the regional rainfall?
None.
We don't have to worry about inflow or outflow.
No, we have to worry about inflow from the glaciers on the mountains that run through underwater and some above ground rivers. The reason why we have San Pedro de Atacama is because the San Pedro River runs through this area, and there are some sweetwater springs, and of course there's some sour or chemically laden springs also. It is a salar. It's just like the Great Salt Lake or any of the great salty basins in the American West. All of the water from paleo lakes evaporated and left all of that mineral behind. So let's zoom in a little bit from Google Earth. And today, let's see, yeah, it's on Highway 23, so that's very nice. It is. There's Highway 23. And yeah, let's just hit that real quick. All right, there we go. Good. Because I like to always live near Highway 23 wherever I go. You'll see that in comparison to the region around, San Pedro has green. That's why it's called the oasis. And there was a lot more green in the past. During the later parts of the 18th and 1900s, 1900s, the actual trees were logged to produce charcoal to produce copper. Because just north and a little bit west of the San Pedro is the town of Calama, which has one of the largest copper mines in South America, the Chusicama copper mine. So they're producing charcoal out of what made the oasis a viable place, which are all the trees. And there are a couple of species of trees of long-lived trees that live there to the day. Chinese moye and chanyar, which produces two different kinds of food. And if you go there, it's absolutely breathtaking, the views. It makes the American West seem like a quaint little place because there's some water there. If any rain does come, it typically comes in the form of about 3 or 4 centimeters a year, and 1 month it'll drop. And then there's nothing left. NASA uses the San Pedro de Atacama region as a testing ground for it's moon rovers, Mars rovers, any type of extraplanetary thing where you need absolutely no life whatsoever. There are places in San Pedro where there is nothing living, even microbial life. It is dead. Because it's been a desert like this for at least 6 million years. So that's a long geological history of being fairly inert. You can see that it has been a place of occupation historically. There was this town of San Pedro de Atacama, which took over and produced a mission to the San Pedro Indians that lived in the area from approximately 10,000 years ago till today. And a large majority of the population of San Pedro are, in fact, indigenous people. However, they did a fairly good job of exterminating the language and the culture of those San Pedro people, so they're now basically the Europeanized mestizo culture that you find all across South America. Let's see. One of the places that's very important in the study is this place called the Valley of the Moon, and it has some really interesting, some very interesting geological formations. Like these are called the Three Sisters, the Three Marias, and you'll see that anywhere when standing in the basin, you'll get this this lovely view of large volcanic mountains. And these are quite high. What's the like 6,000 meters? You know, very tall mountains. I mean, you're already high up, but you know this plain runs up to the foothills of these mountains. And along the slopes, the talus slopes of these mountains, you can find the objects of study, you can find obsidians. And you can even see that that is a flow. And of course, in this area where there's hardly any active erosion outside of wind erosion, there's no water erosion, there's no plant breakdown of materials, you'll see that you can actually really look at the geology close up and see everything, which is kind of nice. This is Lichen Cavor. And actually, it's a walk-up. There's a backside climb that's not a technical climb. You can walk up to the peak without using any technical gear. In the summer, our winter, their summer, you can walk up to the top of that thing if you're so inclined to do that. And another cool thing is that there's a highway. You see that highway? It runs right up here, and then you go that way, and you go on your way to Argentina. So this is a well-traveled road. It is one of the main highways to get materials from the east side of the Andes to the west side of the Andes in the central region. And this has been a highway, a mode of travel since prehistory. And in fact, this highway runs along a known Llama caravan route. Before it was a Llama caravan route, it was probably a foot traffic route for people in prehistory. All right, so let's go back to the top real quick. Current slide. The materials that we're looking at in the study come from the Gustavo Lepage Museum in San Pedro Atacama. Here's the outside of the museum. Here's the rotunda that has these little spurs with galleries displaying the material culture. All this material is collected by a Catholic priest, Gustavo Lepage. He was French, served some time in West Africa, and then was assigned to San Pedro de Atacama. And he ran his town like a good feudal lord, to the point where he was assigning individuals to be married to each other. But that's what it was like. It was the hacienda mentality. It is now controlled by the University Católica del Norte and given a fancy name, but everyone knows it as the Gustavo Lepage Museum. This year, all the materials from this museum are going to be put into storage. It's going to be torn down and a new museum built out of concrete, because this museum is built of adobe. And when it only rains once a year, and sometimes it doesn't rain once a year, you can build out of mud, put plaster, and before it had a fancy metal roof, it was a thatch roof on this building. Because nothing degrades in this environment. Nothing ever degrades in the proper conditions. So this is just a view from the parking lot, just to show you what horrible conditions that you have. Looking out the outside, you can see the beautiful Cordillera And of course, if you look the other way, you can see the other side of the corridor and the other side of the basin. So it's a really nice place to work. Next, why is the archaeology of this region so important? Well, number one, it's believed to have been a type of crossroads for trade between peoples in both the north-south and east-west corridor. That you find materials from northern Chile showing up in places in Peru and Bolivia. And you find stuff from Bolivia and Peru showing up in San Pedro. So that means that there's some type of link between people and stuff, between regions that we think of as a long haul, but it's just a nice month walk for the people in prehistory. A young caravan or a family would just take a nice walk for a month and leave your town and go visit relatives or trading partners in another area of South America, like Argentina, like Peru, like Bolivia, and come back with goodies and stories and maybe a wife or a husband, or you may leave a kid as a wife or a husband. The movement of people and stuff is very important. We find a lot of ceramic artifacts that look similar to types found in other regions. And the region has always been documented to have been important in trading in the past. And today, it is a bustling location for tourists and travel in itself. So the spirit of San Pedro has always been one of transhumance with a settlement, a large settlement occupying different parts of the oasis. So if we look at the region here, this is the San Pedro de Atacama. And the sphere of influence of San Pedro Atacama goes all the way up from the Lake Titicaca Basin, southern Peru, all the way out here into the northwest Argentina area, and down into central Chile. You find stuff from all over this region showing up in burials in San Pedro de Atacama, and that's really nice. This is what the forest looks like right after the rains come. So it's actually quite pleasant. And when we start thinking about the time periods involved, there is an earlier time period called the Archaic, where it was probably small little settlements based around the hunting and gathering of wild resources. And during the formative, the building of permanent structures and residences began, and the production of copious amounts of diagnosable ceramics begins. In the middle period, we see the invasion, or at least the inclusion of San Pedro de Atacama in the Tiwanaku Empire that's based out of the Lake Titicaca Basin. So this is very important for both iconographically and culturally in the development of San Pedro archaeology. And in the late intermediate period, the Tiwanaku Empire falls or goes in decline, and people kind of head toward the hills and develop many different local varieties of ceramics, in which we interpret as a breaking down of a hegemonic or cohesive cultural program and the development of many small local programs, cultures. And of course, in the late period, the Inca arrive somewhere in here, and they set up a tambo, they set up an outpost, and they begin trading. One of the things that the San Pedro actually has to offer in this region is wood and wood products, tree products, and some of the iconographic images or some of the iconographic items of San Pedro Atacama are the objects made of wood that were produced probably here and traded all over South America. Some of the archaeological sites, they're not that impressive because they're made out of adobe, out of mud, and out of the local rocks, out of granites, basalts, rhyolites. And a lot of them are dry mortar, so they're basically just piles of rocks. And inside of these piles of rocks, we believe there probably have been some type of a tent or some type of fabric covering. There would have been a central post in most of these structures with some type of shade, a sun covering. They built up the sides of the mountains, they built out into the plains, and as you see that there's aeolian deposits of sand and materials, but if you just take your little, take a kid's sand trowel and just remove the sand, you'll see everything, just like Pompeii, sitting on the surface. You dig down a little bit, and you'll see all of the trash. And if we get into some of the material culture, you'll see it's quite stunning how much stuff is actually preserved. Now, if you go back to Google Earth, you'll see that this is an outline of the green areas. Each one of these green areas is separated and called an IU. An IU is it's like a clan determination or a clan area. And each one of these little oases has a clan determination. The people call themselves by this clan name or IU name. The two sites that we were looking at, the site of Solor, right here in yellow, and the archaeological site of Coyo Aldea, which is outside the main IU of Coyo, but was probably a lot bigger, but because of people have been deforesting, and these trees, it takes a lot for them to get going. Once you take a tree out, it's like removing an organ from a body. It's really, it's disastrous to the ecosystem. Sequitor, Chikar, Yaye, Larache, Solcor, Conde, Duque, this is the IU that has the main downtown. And Quitor, there's some beautiful Middle Horizon and late intermediate period settlements up here in this area. Tulor, Beitor, Pukunching, and Kukuter. These are kind of outlying areas that each one of these oases, or little separate oases, they're literally covered in artifacts. It's covered. There is no archaeological site per se. What it is a greater concentration versus a lesser concentration of stuff on the ground. So when you walk on the area, you'll be walking across archaeological materials. This is what Solor looks like when you go to it today. You'll see all of these Polylepis, Shinesmoye, Chanyar trees. People use this area for grazing goats and sheep. There's very few llamas actually in the area. And each one of these little bumps here, you see these little bumps, those are little grassy, little patches of colony grasses. Underneath that is probably some archaeological remnant. A burial, a hole, a trash pit, something where the ground surface has been disturbed and roots are going in there and absorbing organics out of that soil. So it's actually quite interesting. If you want to find stuff subsurface, you just go to these little mounds and that's where they are. Now this doesn't look like much when you just look at it from the highway, but then when you take a little close up, you're like, oh, the place is filthy with artifacts. Rocks, ceramics, bones, it's just covered. And depending upon how the wind is blowing, this stuff can be covered and uncovered within a season or two. What's really spectacular is the amount of preservation of the stuff. That the San Pedro de Atacama Museum, I personally photographed 4,000 of these objects. And these are just the whole vessels that they have, their whole corridors and rooms of bodies, gourds, tapestries, hats, ponchos, sandals, mummies, woven baskets, everything. And of course, I haven't gotten into this, but there's a really nice collection of paleofeces. Not coprolites, because they're not dinosaurs, but paleofeces. So if you want to do direct dietary reconstruction of people, you just have to look at the paleofeces and determine what might be in there and what have gone through the digestive tracts of both people and animals. The distinctive style of San Pedro is this beautiful burnished blackware. And it looks like it has a slip, but this is caused primarily by producing a smooth surface and then through successive rubbing, producing this beautiful burnished look. They come out of the ground like this, which is kind of nice. You don't have to do much in the way of conservation. And this is an interesting story we're tracking down, but the little white dots inside of this, it's titanium dioxide. And you might know titanium dioxide as whiteout. It's a very rare chemical, a very rare compound that they were using to decorate their ceramics. That's koyo incised and koyo punctated. That's the type. So this is the stuff that is named after the primary site, the Koyo Aldea area, or Koyo. You find this in high proportion in that area. And of course, they're doing red wares, they're doing big coffee cups, they're doing mugs. And these, I love these little guys. These are anthropomorphic bottles. These are only produced to be put with burials. They don't use these as everyday items. You don't find them in domestic trash. You find them as whole objects in burials with people. And you see they have this kind of, style, this like little death head style, little faces. And there is a typology to this. These are the most distinctive that conform to the types, but there are intermediaries in between here that we could probably use to produce a seriation of how these things changed over time. And as you can see here, if you look at this through time, this is a style that comes from the Lake Titicaca Basin. So when I was working in Bolivia, I would find this stuff. And then go to San Pedro, oh look, it's the same stuff. And one of our questions for another study is to find out whether this is conforming to a style made of local material or if it is an extraneous material brought in as a trade item. And you can see how in the middle period the styles change, in the late intermediate period they get away from the elaborate burial furnishings that they were producing in the middle period, and they go to simple stuff. And here's just an example of what you might find if you open one of the burials. Very little biological degradation. So here's just an average mummy. Just an average one. This isn't even like a good one. The good ones are very nice. And of course, if you want to do x-rays and physical anthropology, it's all there. Here's a rope, right? You see that? There's a nice belt, baskets, ceramics, hair, which is also good for chemical reconstruction. So there are thousands of human burials. LePage was very, very interested in collecting every single buried human he could get his hands on and putting them into the museum. Thousands of artifacts that don't survive in other locations, like hand-woven baskets. You find this in the American Southwest in caves and in very arid locations, but you don't find it everywhere. This gives you a really great look at the material culture of these people. It has a very long time depth of occupation, and a set of local museums, not just the museum in San Pedro Atacama, but in Toconao and in Calama and further down, you find little local museums where people have collected all this archaeological material and made it available for people to research. So I've already talked to you a little bit about what obsidian is. It comes from a magma flow, and it's approximately 70 to 75% silica dioxide, a little bit of magnesium and iron and some other compounds. And it can be used to make all kinds of artifacts, and we'll see some of those artifacts later on. And of course, if you want to look at the geology, obsidian occurs in these little flows that occur after a magma chamber is erupted, and you have little spurs of this that open up from these magmas rushing out and then crystallizing rapidly on either on top of the surface or just below the surface. If you want to go see obsidian being made today, go to Iceland and Hawaii, and you'll see it being made by the earth. Now, archaeometry is a subset, or it's a special part of archaeology, and that is using chemical and physical techniques to investigate archaeological artifacts. Every single instrument that you can think of to investigate materials has been used by archaeologists to some effect, because just like any good forensic anthropologist or an investigative researcher, we want to use everything that we can to investigate our materials. We perform it everywhere, field, museum, laboratories, and manufacturers of instruments to supply industry with mobile instrumentation. Also they fund us with the use of instruments that cost tens, twenties of thousands of dollars to own. They let us borrow these things and use them in the field periodically. And of course, we use all these techniques in conjunction with traditional archaeological methods and anthropological methods. So we wanted to select a large number of obsidian and other lithic objects from the collections of Solor and Koyo Aldea and perform photography, portable X-ray fluorescence, and Fourier transformation infrared spectrometry, which has different, these are different techniques obviously, 3 different kinds of photonic techniques to investigate these artifacts. And of course create a database of this information for future research. So here's just a little bit of a sample. This is a sample from Koyo Aldea. I went through all of the collection bags and I picked out all of the pieces of obsidian that were greater than 2 centimeters across the X and Y axis. And of course, solar, someone went across that solar IU and collected about 15,000 projectile points. And it was in this nice long box and 6 bags. And each bag was about 3 kilos of nothing but projectile points. So we decided to sample this bag and pick out representative material types and styles of projectiles. And you can see just by looking at it, there's tons of different styles of these projectile points. Yeah?
How big are these dimensions?
Oh, you'll see that, but mostly about 2, 4, 5 centimeters, not that big. These are true arrowheads, by the way. These are bullets, basically. They're not for spears, they're not knives, they're not ceremonial. These are just everyday pedestrian, I need arrows. And the quantity that's produced makes me believe that this solar IU is probably a primary producer of these projectile points, not only for San Pedro Atacama, but for other areas. Now this is important, other areas. Where can we find these objects in other places? So let's talk about the electromagnetic spectrum. Carrie, you know this, right? Yeah. So, photography. Fourier transformation infrared spectrometry, portable X-ray fluorescence. We don't do anything with ultraviolet, but there are tons of applications for gamma rays, ultraviolet, even microwave and radio wave investigations in material culture. It's just what do these wavelengths, what do these photonic energies do to materials, and how can we then take the internal properties of those materials and then back translate what are you, how are you made, what are you made of? So the first is X-ray fluorescence. I talked about this last year, last academic year, so I won't go into that deeply, but it's a technique using soft X-rays to excite and expel electrons from the K and L shells, and then when electrons from further out fall back in, they release an X-ray of a known quantum or a known energy. You are exciting the atoms in the material, having them kick out electrons, they're replaced by other electrons, and because of conservation of energy and motion, a reciprocal X-ray is emitted. And that's what you detect. So you excite it and you detect it, and then depending upon the exact element, it will produce a signature photon, or a set of signature photons. You then transform that into a curve, and you can start determining what type of materials or what type of elements are inside of your material. So it's a fairly nice little technique that people use all the time for composition analysis of materials. It's spectacular for obsidian because the primary constituents of obsidian you can't see with X-ray, with PXRF. So it's like having an invisible medium in which metals and trace elements are floating. The next is IR spectrometry, and this is it's an emerging science. It's been used a lot to investigate organic compounds because it primarily excites dipolar molecules like hydroxyls and anything that has some oxygen in it or some carbon or some hydrogen. This technique works with quite well. It's actually interesting. Covalent molecules and molecules that are not dipolar, it just sees right through it. So that's kind of neat. X-ray spectrography works on the principle that IR makes molecules, not elements, not atoms, makes molecules vibrate. And because the vibration in itself is quantized, there's a quanta to it, you can actually use this to determine different kinds of molecular bonds. And there are multiple types of bonds that it excites, and it produces a spectra for these different kinds of bonds. So when you look at obsidian, you have some primary profiles of your water and hydroxyl groups and silica oxide, which is what the primary component of obsidian is. So if you're trying to diagnose a rock, you can use IR as a rapid investigation because there are lots of rocks that are black and shiny. And some of them are not obsidian. And some obsidians are not black and shiny, but they're gray, they're green, they're clear. They look like mahogany wood. They're red. They're all kinds of different colors and textures. So some things that are obsidian are classified as other things. So you can use IR to rapidly assess what material you have in the first place. And you can look at a whole collection of lithics and start putting them into piles by material type. So we did this analysis on about 1,600, a little more than 1,600 objects. So we're looking at a very nice database of information. And doing the analysis, here's photography. This is obsidian that comes from the area around the flows that generated Lycabor and Sycamore, the two mountains, the two volcanic mountains. They are geologically distinct, each flow, because as the magma rises through the mantle and it rises through the upper part of the crust, just before it extrudes, it picks up trace elements from its surrounding rock. So each flow itself has a subsignature within a larger signature. So we're calling this the Tara Obsidian Group because there's a well-known obsidian flow on the backside of Lycabor, almost to Bolivia, that's called the Tara Lake, and there's a Tara Obsidian. And it looks like this. It's a nodular. It has a reddish oxide cortex, and when you break it open, it has this beautiful black, smooth, amorphous interior. And as you can see, here are just some of the elements that we can diagnose this Tara Obsidian with. And you'll see titanium, manganese, iron, zinc, rubidium, strontium, and zirconium. These numbers, you can use this and other numbers. There's about 12 other elements that you can use to produce a profile of what this obsidian is like. Now remember, because of instrumentation and because of variability within the material, it is not a number. What it is a group of numbers. That's going to be important when we look at all the data together in later analysis. And right here, this is a spectra from FTIR. Now, classically, it is used as an emission, or not emission, but an absorption profile. The detector head that we had on ours does diffuse, so we actually get emission, it gets absorption and emission in IR. Because sometimes the IR photon will excite a bond and it will emit a photon. So you can get absorption and emission in specific quanta. And this is reciprocal centimeters. This graph right here, reciprocal centimeters of the wavelength of the photon. And I'll just point out some distinctive areas. This area right here, around 3600, this is, if you go back to that original chart, this is where hydroxyls and some of the water emission lines are. Right here, this is where another little bit of water is. And right here in this area, this is where silica and silica oxide compounds are. Right here. So there's a distinctive valley with a hump, with a long peak. So you have a peak, a little hump, and a valley. This is very distinctive of obsidian. And a lot of these techniques, you look at libraries of different kinds of rocks, you'll see that it's primarily, it's a percentage match to a rock type. But good, thankfully for us, that those rock types do vary a lot in the type of spectra they produce. And of course, these are just some of the wavelengths that you can look. You can go actually further out and a little farther in if you like. Now, this is a well-known obsidian source that everyone talks about and knows about in the area. This is a new obsidian source, the Valley of the Moon. And this Valley of the Moon source is not from a classic flow, but it's called a secondary source, where glacial till and the movement of sediments containing obsidian moved this obsidian from somewhere else and placed it in a valley. So from a volcanic flow somewhere else, this stuff came along for the ride and was deposited in basically in a Pleistocene scree slope. This Valley of the Moon is clear to greenish, and of course it has low iron. It has a low iron signature where if you go back, this has a medium iron and there's high iron. This low iron group is distinctive, and this has a little more water here, and that's because this silica oxide, just like glass, it will start to degrade by water molecules grabbing onto some silica and pulling it off. So it gets a hydration layer and it builds up this cortex. And that's something that archaeologists use to determine the age of an artifact since a fresh surface was produced. How old is it by how much water has penetrated into the surface of the obsidian? So this little water peak, these little water peaks are actually fairly indicative of obsidian that has been on the surface or has been degrading for a long time. Like in Cabora obsidian, looks like the Tara stuff. This is an obsidian from a different flow, but in the same area. Peaks, like we've seen before. Here's an artifact. This is from Solor. And you'll see here, oh, look at that. That has a big water peak. Big water peaks on the surface of this artifact. And if we were to standardize this and to reduce either the other peaks or inflate the other peaks, we would be able to tell. We would probably be able to tell by geological, or not, by chronological age, if there's a profile we could produce for how much hydration is on the surface for these artifacts. This is a low iron group obsidian. Mahogany obsidian, red and black together. Color in obsidian is formed primarily by iron oxides and hydrated oxides of iron inside of the matrix. It has nothing to do with overall chemical elemental composition. It has everything to do with how those elements are distributed. So that granite, you know that there are many different colors of granite, pretty much all the same, but this is red. You can get red streaking in obsidian, just the way that you can get white streaking. Actually, snowflake obsidian is obsidian that has a high amount of water in it, and it produces those stars inside of it. Interesting. Tara group, another type, huge amount of water. This is not a clear obsidian. This is an opaque obsidian with a granular structure. Kind of like rhyolite, but still looks like an obsidian. And it is of the high iron group. And here's another one. This is a black opaque obsidian, high iron, same stuff. This we thought this was a red obsidian. Glassy, really nice, conforms to a red obsidian color. It's church. That's a cryptocrystalline. You can tell, like, oh yeah, that looks nothing like the profile of obsidian. Because these are different silica compounds inside of this. And depending upon the complexity of the church, this graph looks like seesaw mountains as opposed to two big peaks. So, what do we want to do? We want to then start to analyze this data. And what does this data as a group start to tell us about the obsidians that we're studying? This is first pass data. First of all, we're going to do some histograms, and then we wanted to do some elemental analysis. And most people use principal components analysis when they do analysis of obsidians because it accepts multiple variables and helps reduce variables down into what are, human terms. You put in 15 variables, it produces 2 or 3 synthetic variables that you can then easily graph and visualize. Principal components analysis, it's voodoo statistics. You have some ability to control the voodoo, but it's kind of a black box. Numbers go in, and you can play around with some of the dials, but but most of the time I don't want to do the math, because in the math would be horrendous to do. So here are our results. Nature is good, because nature, in this case, produced 3 different groups for us. Low iron, high, medium iron, and high iron sources. This high iron is actually it looks like obsidian, but it's the little valley with the little hump in the valley is slightly skewed, so it doesn't look exactly like an obsidian. It looks kind of like a transition between obsidian and rhyolite, but it has a high iron, and it's from an unknown source. We don't know where on the landscape it comes from. The next is this medium iron group, the Tara group, the stuff around Lichen Kabor, the big mountain, the big volcano. And the stuff here, low iron, from the Valley of the Moon. There are many different colors, but it's a low iron obsidian type. You probably would not get low iron obsidian from this flow. This is a different flow. We don't know exactly where the flow originates, but we know where you can get it in the landscape. These are all the results from Solar. The site of Solar, this is the 15,000 objects. This is, we go back, I think it was something like 1,200 projectile points for this. 1,000 projectile points. You're looking, yeah.
What are your axes?
Oh, this is iron, and this is just number of objects with that iron count. So it's just a histogram of parts per million iron, and then number. It was kind of, I know for science we should have the scale of the y-axis, but rhetorically it looks good. It does. It looks good.
Don't tell them what they're looking at.
No, well, this is here's the iron group here. Iron along the y-axis, number of objects with that iron signature. These are from Coyo Aldea, the little village that was investigated by great-grandpa Emily Stovall in the 90s. They dug up all this stuff. It has the low iron group, it has the medium iron group, and some of the high iron group. But you'll see that the percentage representation is different. There's more of the medium iron closer to the mountain. And there's more of the low iron group closer to the Valley of the Moon. And if you put all that information, a ton, or you put in 1, 2, 3, 4, 5, 6, 7, you put in 7 elements into a PCA, it produces nice, tight groupings. Groupings based upon, these are the axes, wherever it pulls the axis. This is group 3 down here. These are all the low iron obsidians. If you do this with the medium irons, you get a glob with hardly any resolution. And to do resolution on that, you probably have to go to extremely rare earth elements like iridium and yttrium and other ones that are very, very tiny components, below the parts per million to get any type of resolution on those. And then you have to destroy the object, and this costs a ton of money, so we're not going to do that. But for this low iron group, you'll see that there's lots of different flows here. Each one of these is probably a different flow. This is maybe one flow. Here's a flow, there's a flow. All of these are different obsidian flows that got mixed up probably in this glacial till. Stuff streaming into this from this glacial movement of sediments and obsidian and other rocks deposited in the Valley of the Moon. There you go, right there.
So these aren't artifacts.
These are artifacts. Yes, these are all. Each individual point is an artifact.
A spearhead.
A spearhead, yeah, one of those little arrowheads, or a flake. So when you look at this right here, you'll see that this is for all of those low iron groups from Solar, from the site of Solar. They're getting low iron obsidian from somewhere else. Or they're getting it from, and because this is percentages, because we did a lot more Solar, we're getting more rare stuff. But the majority of these, because you're seeing multiples on top of each other, the majority by a slim margin is this group 3 Valley of the Moon obsidian. And the reason why I call it Valley of the Moon is because I picked it up from the surface of the Valley of the Moon. And there's GPS coordinates, like this is where this thing came from. And pick these up off the surface. And I know exactly where they came from. That's why I can say that's a source. And then for Coyo Aldea, there it is. The majority is Valley of the Moon and some other smaller representations. But these are the same colors as the solar group. Maybe if we were to sample 1,000 Coyo Aldeas, we might get the same profile of this, same proportions. Now, what's important? Let's go back to Google Earth real quick. Go back to Google Earth and you'll see, let's hide the imagery. Let's go back here. Before we started doing this work, most people believed that the obsidian that was found in the sites around San Pedro de Atacama was coming from somewhere else. They thought it was coming from Peru. They thought it was coming from Argentina because there are some well-known, well-documented sources of obsidian in Argentina, and we have ceramics from Argentina. They thought they were getting their stuff from somewhere else. What this study shows is that the majority of all the obsidian used to produce artifacts in San Pedro de Atacama comes from, here's the Valley of the Moon, here's Coyo Aldea, here's that, you see that right here? That is that little extrusion right there, that's that little sediment right there. That's where I picked up the obsidian. That is about 3 to 4 hour walk. 3 to 4 hour walk. Send your kid out in the morning and go get some obsidian and bring it back by dinner time. And if you wanted to go get obsidian from, here's Solor, right here. Here's Solor, right there. The highway cuts through it. Here's the mountain. Take you 1 day to get there, get your stuff, and come back the next day. In prehistory, that's nothing. That's a little jaunt. So what we're proving is that when it comes to obsidian resources, people use stuff locally, and what I'm actually interested in is how much of this stuff leaves the San Pedro de Atacama Basin and shows up in other sites. So that's why we have to build up a large number of determinations, and then people can compare their stuff to our stuff. And since we know that this is where it comes from on the ground, we can prove that our stuff is locally placed to our volcano there and to our little valley. So if you find San Pedro de Atacama obsidian over here, let's say in, Argentina, we could say that we have direct travel, direct trade of people. And that's not that big a deal. And in fact, there's lots of ceramics that come from the area called Buki and Salta that show up here in San Pedro Atacama. I'd love to see if anyone has found obsidian from us in their area. And then just to go back, I already talked about this. Future research. I want to discover more obsidian sources in the basin. I want to try and create a local typology of the projectile points because no one has done this. They've done it for the ceramics, but they haven't done it for the lithics. I want to use obsidian hydration to date some of these obsidian artifacts, and then I want to produce this comprehensive database. And of course, Fond du Lac students can help with this. So thank you for your time, and that's my talk.